When you expand quadratic numbers into simple continued fractions, something pretty amazing happens. A pattern appears. This video is about the pattern that appears when we expand square roots. We'll describe the pattern and discuss examples. Let's get started. First, let's look at a representative example. The square root of 19 equals 4, 2, 1, 3, 1, 2, 8, with a bar over everything except the 4. The first term is non-repeating, but the rest, everything under the bar, repeats indefinitely. It's somewhat surprising that a repeating pattern appears at all, but there's more. Within the repeating part, the terms before the last one form a palindrome. You can read it forward or backward, and it's the same. 2, 1, 3, 1, 2, 2, 1, 3, 1, 2. And the last term is twice A0. In this case, 8 is twice 4. It's hard to believe, for me at least, that if we take the square root of any non-square positive integer and expand it into a simple continued fraction, the same pattern will appear. The initial term is non-repeating, and the repeating part includes a palindrome, followed by a final term that equals twice the initial term. Let's jot down a general characterization of this pattern. We can write the simple continued fraction with variables like this. The square root of x, where x is an integer but not a perfect square, equals a0, a1, a2, and this continues to some an minus 1 and ends with an. We put a bar over a1 through an. Here's the pattern. The first term a0 is non-repeating, but the rest, a1 through an, are repeating. Within the repeating portion, a1 through an minus 1 form a palindrome, and the last term an equals 2 times the first term a0. When continued fractions have a repeating part like this, sometimes we say they're cyclic or periodic. These are just different terms you might come across. And the word period is used when we talk about the length of the repeating portion. For square roots, the period is always the length of the palindrome plus 1. Stop the video and see if you can figure out the period for our example, the expansion of the square root of 19. The period is 6. The repeating part has the palindrome, which is 5 terms, and then there's an, which is one more term. So there is a total of 5 plus 1 equals 6 terms in the repeating part. So the period is 6. Okay, let's shift gears now and look at examples. Here's a table. It has some values of x in the first column, and the other two columns have the square root of x expanded into a simple continued fraction. This column has a0, the first term in the expansion, the term that does not repeat. And this column has the repeating part. When you read the first row, where x equals 2, you should interpret it as saying the square root of x when x equals 2 is 1, 2, with 2 repeating. This is the 1, the non-repeating part, and this is the 2, which is the repeating part. And the next row says the square root of x when x equals 3 is 1, 1, 2, with 1, 2 repeating. This is the 1, which does not repeat, and this is the 1, 2, which is the repeating part. One more. When x is 19, the square root is 4, 2, 1, 3, 1, 2, 8, with everything but the 4 repeating. It's our example to the left. Stop the video and make sure you understand the table. And notice the pattern in the expansions. The repeating part has a palindrome followed by a final term which equals twice a0. Do you notice anything interesting or anything you didn't expect? We'll make a few notes about the expansions, focusing on the palindromes. When x equals 2, the palindrome is the empty set. There are no terms before the last one, which is twice a0. I wondered if empty sets are considered palindromes. It seems like that could go either way. Empty sets are considered palindromes. When x equals 3, the palindrome is a single term. I wrote digit on the screen, but term is a better word. Other numbers have palindromes like these. In fact, there are infinitely many of both of them. In this table, though, the square root of 5 is the only one with the empty set, like the square root of 2. And 6, 8, and 72 have a single term, like the square root of 3. When x equals 13, the palindrome has an even number of terms, but is not the empty set. 13 is the smallest number with this type of palindrome. There are infinitely many of these too. When x is less than 100, though, there actually aren't too many like this. We included a disproportionate number of them in the table. The numbers are 41, 53, 89, and 97. The expansion of 94 has the longest palindrome out of the numbers less than 100. Its palindrome is 15 terms long. You have to go to 139 before there is a longer palindrome. That one is 17 terms long. As a general note, as we increase x, we can find longer and longer palindromes, and therefore longer periods. But we can also continue to find short palindromes. For example, no matter how large of an x you might pick, there's an infinite set of integers that are larger than x and whose palindrome is the empty set. We'll add this type of expansion, where there is just one repeating term, to our general characterization. In these cases, n equals 2, the palindrome is the empty set, and the period equals 1. In this video, we describe the pattern that appears when we expand square roots into simple continued fractions, and we discuss some examples. That's all for now.